Okay, I think we can start now. So let me share my screen first. Okay, so today we are going to look at the main algorithm of Rsa Crypto System. But before doing that, I will just recall what some important things from the last class. So I think we first of all, you remember this result: if a and b are integers, then there exist s and t integers such that GCD of a and b is equal to s of a plus t of b. That's one result. You know, if GCD of a and n is 1, then the equation ax congruent to b mod n is solvable and its solution is unique. Okay, this is another result. Okay, and then we have this Fermat-Little theorem that a raised to power p minus 1 mod p is 1 in ZP. Okay, if where p is a prime. Okay, and then we had this Chinese remainder theorem that if we have a system of equations, then we can actually solve the solution as a product of all these mi's. Okay, and solution is something like this. So now let me start. Okay, so Rsa Crypto System. Can you see my slides? Anyone?
Yes.
Yes, sir.
Yes,
Okay.
sir.
Yes, sir.
Okay, thank you. As I told you, and I gave you an example, how by using two locks, basically, you can do the this public key crypto system was developed by Deff and Hellman in 1976, and based on those ideas, RSA crypto system was built. Okay, and so let me. So there are two people, Alice and Bob, who wants to communicate. So first of all, there is Bob's algo that I would like to look at. What is Bob's algo? First, choose large prime numbers. So there is a preparation for Bob's, how he can receive a secret message. So for that he has to do some preparation. So first, choose large prime numbers P and Q. Okay. Then compute the product of these two prime numbers. Call it N, which is P into Q. Third, what Bob does, choose a number E which is not equal to 1 such that GCD of E comma P minus 1 P minus 1 into Q minus 1 is 1, and this E is known as exponent. Actually, choose a number E not equal to 1 such that GCD of E and P minus 1 Q minus 1 is 1. Then fourth, compute D, which is inverse of E, mod P minus 1, Q minus 1. Mod means modulus, we are reducing it modulo P minus 1 into Q minus 1, and whatever is the remainder, that is the inverse. So that means E into D are inverses of each other, right? So D into E into D is equal to 1, mod P minus 1 into Q minus 1. Now Bob is ready and he publishes two keys, publish E and N. Okay, on maybe on your website or whatever, you publicly this is known to everyone. E is the exponent and N is the number, product of these two prime numbers. Okay, this is published. So this is known as public key. Public key, sort of a lock, a public lock. And 6, keep D as a secret. So D is nothing but a private key. Private key, so private lock, or so there is a private key. So basically private key and public key, there are two keys. E is a public key, D is a secret key. Okay, so I hope you understood the Bob's preparation on his site. He choose two large primes P and Q, compute N is equal to P into Q, choose an exponent E not equal to 1, such as a GCD of E and P minus 1, Q minus 1 is 1. Compute D, which is inverse of E, modulo P minus 1, Q minus 1. Publish E and N. So E is a public key. And keep the D as a secret. Now, even if N is known to everyone, they don't know the prime factors P and Q. Okay. So now, what is the next step of the algorithm? Alice wants to send a message. Alice is sending message X to Bob. Now what Alice should do? She will first read the public keys of Bob, right, which is E and N. First, she will read E and N. Then second, she computes X raised to power E, call it Y. She computes Y, which is a number, X raised to power E, the exponent, whatever is the message X, raise it to power E, modulo N. And then, so she is putting a lock on the message using the public key of Bob, right? Using E and N. Okay. Now, send Y to Bob. Okay. Now, fourth thing, Bob receives Y from Alice and compute. Well, Bob wants to read the message. So what he does, he computes Y raised to power D. I call it as a Z. Whatever Y is received, raised to the power D. D, remember, is the secret key of Bob, modulo N. So what happens? This algorithm will work, and actually, then he reads this Z. This works, this algorithm will work if we show that Z is equal to X. First of all, do you agree or not? Please unmute yourself and answer me. Any of you?
Yes, sir.
Yes, sir.
Yes,
Good.
sir.
Good. So now you understood the basic idea how Bob has done a preparation of public keys E and N. Then Alice is sending a message X to Bob. Okay. We compute Y, which is X raised to power E modulo N, send Y to Bob. Then Bob is raising Y raised to power D and storing it Z, right? I will show you now that Z is nothing but actually X. And so that means this algorithm is working perfectly fine. So let us see that. So our proof of this algorithm, I have to show that Y raised to power D is equal to X. So now Y raised to power D will be what? Y is X raised to power E raised to power D. So this is nothing but X raised to power ED mod N, right? Modulo N was there. Now, since there is a condition GCD of E and P minus 1, Q minus 1 is 1, right? This implies that E into D is equal to 1 mod P minus 1, Q minus 1. From the previous result, this will happen. Since GCD is 1, we have ED is equal to 1 mod P minus 1, Q minus 1, right? So there exists a solution D, right? So that's why this is there, right? Now that means because E and D are inverses of each other anyway. If you look at the preparation, right? E and D is equal to E inverse. So that means E into D is equal to 1 mod P minus 1 Q minus 1, right? Okay, this implies that there exists K, integer K, such that E into D is equal to 1 plus K times P minus 1 into Q minus 1, because it is modulo with P minus 1 Q minus 1. So that means ED minus 1 is a multiple of P minus 1 into Q minus 1. So that multiple number is K. So ED is equal to 1 plus K into P minus 1 into Q minus 1. So now we look at Y raised to power D. It turns out that Y raised to power D is equal to X raised to power ED, which is same thing as X raised to power 1 plus K times P minus 1 into Q minus 1, right? This can be written as X into X raised to power K times P minus 1 into Q minus 1 and mod. This is there, right? I have just substituted the value of ED here, which is this. Now I'm now focus on this quantity, X raised to power K times P minus 1 times Q minus 1. So Y raised to power D will be X. If I somehow I can show that this value is nothing but 1. So how we can show that this value, this quantity is 1? And if you can show this, then our job is done. Okay. So now again I am using Fermat's-Little theorem. Since GCD of X and P is 1, we know that X raised to power P minus 1 is congruent to 1 mod P, right? Similarly, GCD of X and Q, P and Q are primes, you remember, is 1, then X raised to power Q minus 1 is congruent to 1 mod Q, right? So therefore, now this quantity Y raised to power D can be written as X times X raised to power P minus 1 raised to power K times Q minus 1, right? Now X raised to power P minus 1 is congruent to 1. So this is 1 raised to power K times Q minus 1, which will be 1. So this whole thing will be X into 1 mod P, right? And also we can see that Y raised to power D is similarly x times x raised to power q minus 1 times k times p minus 1, which is nothing but x times 1 mod q, right? Got it? So this is also x, this is also x. So y raised to power d is congruent to x mod p and y raised to power d is congruent to x mod q. Hence, by Chinese remainder theorem, we can say that y raised to power d is congruent to x mod p into q, the product, right? Which is nothing but x mod n, right? And so we are done. So that means y raised to power d is nothing but x. So this algorithm is working. That's what we wanted to show. This is our z actually. Z is equal to y raised to power d. Remember, this is what we wanted to show. Y raised to power d mod n is nothing but x. Okay. So our algorithm is working perfectly fine. This is the beautiful algorithm, right? So we have used Pharmaceutical Theorem and this GCD business to show that this algorithm works. So this is all about RSA crypto system. So now this exponent and this n, I can show you maybe. Can show you that it works here on any secure site. If you see, for example, in this one, show certificate, go to details, you can see that here RSA crypto system. So this is the thing. Yeah, exponent is given here. E is this. E size is 2048 bits, right? And this is the signature. Okay. So this is what you can do. You can see in the any secure website, you will see this. Okay. Okay, so I think that's all for RSA crypto system. Now I think I would like to start, because this was the something that was left over from the last lecture. Now I'm going to start something, a new
Hello,
topic.
sir.
Yes, yes.
Sir, here what was X?
X was y raised to power d.
No,
X
no,
was
means what
no
was
X was
meaning?
the original message. X was the original message that was sent by Alice to Bob. Okay.
Okay, sir.
Okay. I think somehow I lost the writings, but if you want, I can again open it in the form of notes, because we do have notes here. So yeah, so if you have any question, you can ask. Yeah, you see. So here is the RSA crypto system, right? D publish E and N. X is the message which Alice wanted to send to Bob, right? Okay, got it?
So, sir, X
Yes, sir.
cannot be multiple of P or Q. Means, is it the
Oh,
case it is multiple of P or Q? Then if it is, then GCD won't be 1, no?
yeah, so that's yeah, GCD is one, so that is not a multiple rare, correct.
Yeah.
So now actually I have given you an exercise in first assignment to implement this algorithm. Choose X to be some number, okay, and you can choose small numbers. I mean, if you take long numbers, probably difficult implementation will be a little bit clumsy, because the computations will take more time. But anyway, so you can actually do these things and implement it and send the messages. You will enjoy it, okay. So implement this algorithm. This is what is we asked for in the assignment. Okay. Correct? So now, any more questions about this?
Yes, sir. In when we applied Fermat's theorem, then we get x raised to p minus 1 is equivalent to 1 modulo p and 1 modulo q. So, sir, this doesn't implies that x raised to p minus 1 is equivalent to 1 modulo n.
Yeah, that's what I'm saying. See, x raised to p minus 1 is congruent to 1 mod p. That means what happens? You see, y raised for d is nothing but x times x raised to p minus 1 times k times q minus 1. Right? So this internal quantity is 1 mod p. So if this internal quantity is 1, that means this is x times 1 raised to power k times q minus 1. This whole thing will remain 1. So y raised for d is congruent to x mod p. Similarly, you can show that y raised for d is also congruent to x mod q. Okay. Now using Chinese remainder theorem, y raised for d is congruent to x mod p into q. Okay, which is the product of these two, which is n. Okay.
Yeah. Okay.
Yeah.
Sir,
Yes.
sir, here y raised to d is equals to x raised to ed mod n means mod n is on both the sides.
Yeah. Modern means whatever y raised for d is coming, we are reducing, we are dividing by n and looking at the remainder. Remainder turns out to be x from y raised for d.
This
Okay.
can be true only if what we say x is not a multiple of p and q simultaneously, right?
Yeah. So that's GCD is 1 anyway. That is given here, right?
Yes.
Yeah.
Yes. Okay, sir.
Okay, so now I think that's all for RSA crypto system. Now I am going to talk about a new topic known as 1 minute logic. Any idea what is logic? Where we use logic? Topic is logic. Who
Sir, we
invented
use
logic?
logic for kids.
Huh?
We use logic in computers for decision making.
Good. Yeah, there are plenty of applications. But see, whenever I pick up any topic, I ask a question to myself, and I think I am asking the same question to you. Who invented logic? Where it was invented? Any idea?
Aristotle.
Well, I think you all people are trained in Western education system, right?
Sir, in Buddhist invented.
Actually, in
Buddhist
India,
invented
logic
first.
is the oldest known history for logic is in India. Actually,
Yes.
so
Yes.
there are many school of thoughts in India in the logic. So read some history about it. Then you will find all these Western philosophers came later on. So there are different kind of things. People call it zero order logic, first order logic, second order logic, third order logic, and so on. Depending upon their complexities and so on. And there is also what is known as descriptive logic and so on. So now I think in our course we are going to do only two logics. One is propositional logic and second one is predicate logic. Okay, so these are simple things to study. So I'm going to start the propositional logic first, and I will ask you some interesting questions here. Okay. Propositional logic. What is propositional logic? So which deals with propositions, right? So what is proposition? Proposition is a proposition. What is proposition? It's a declarative sentence that is either true or false. Okay. So a declarative sentence which is either true or false is a proposition. Example, but not both. Okay. Example, 2 plus 2 is equal to 3. Is it true? It's a statement, right? Is it true or false?
False.
False. 1 plus 1 is equal to 2. Is it true or false? True. So these are true. Very good. Now, I think as soon as I give this definition, so I'm always thinking about something interesting. So there is, suppose each of you take a piece of paper, right now, while in the class, take a small piece of paper, and on one side of it, write down the statement on the other side of the paper is true, and turn the paper and write down on the other side the statement on the other side of the paper is false. Then what will happen? Anyone can tell?
Paradox.
Paradox. Right. So now if you assume it is true, then it is also false at the same time. So there are statements, there are systems which creates problem, right? So in these propositions, we are, these propositions are either true or false, but not both. This is an important thing. Okay, but not both. Okay, so normally propositions we write down like P, Q, R, S, and truth values are denoted by true or false, T or F, true or false. Okay. Now, if P is a proposition, then we can define what is known as negation of P. It says negation of P. What is negation of P? So, or sometimes in some books you will find P bar as well. So, that means it is not the case that P, right, or not P actually. Okay. So the truth value of negation of P is opposite of the truth value of P. So suppose proposition P says that today is Friday. So what is negation of P? Today is not Friday, right? That is negation. So in fact, I can describe these things with what is known as truth tables, and these are very useful things. Truth tables, we also call it TT, truth tables. So the first, I can define negation of P. So if P is there, then we have negation of P, and I can make truth table. P is true, negation of P is false. If this is false, then this is true. Okay, this is known as truth table. Next, we can do couple of more operations by combining certain propositions. So we can define what is known as conjunction, P conjunction Q. We also sometimes call it as meet, P meet Q. Okay, it's conjunction. Proposition. So it's truth table. Let me describe what is conjunction. So if P is true, Q is true, meet is true. If it is true, one of them is false, then this is false. Okay. If this is false, this is true, then this is false. And if both are false, then this remains false. So if one of them is false, this conjunction will always be false. Okay. And it is true only if both are true. So this is known as conjunction or meet of two propositions. Example, P statement could be today is Friday, and Q is it is raining today. Okay. So true. So this is so P conjunction Q will be today is Friday and it is raining today. Okay. So true, this conjunction is true on rainy Fridays, and it is false on any day that is not Friday. And on Fridays when it does not rain, it will be false. Okay. So this is conjunction. Okay. Next, we define what is known as disjunction. P join Q or P disjunction Q. Sometimes in some books you also notation is P or Q. Okay. So what is the truth table for this? P Q P join Q. So if P is true, Q is true, join will be true. If one is true, if one of them is true, this will remain true, right? If this is false, this is true, this will remain true. If both are false, then only it is false. Okay. So this is a truth table. If you take the same example, right? So P join Q will be today is Friday or it is raining today, right? So this is true on any day that is either Friday or a rainy day, including rainy Fridays. False on days that are not Fridays. That is when it does not rain. Okay. So this is disjunction. Fourth operation is exclusive. Exclusive means P exclusive Q. So the truth table for this is P Q P exclusive Q. So this is true. If P is true, Q is true, then this is false. If one of them is false and true both, if one is true and another one is false, this is true. If one is false, this is true, and if both of them are false, this is false. So P exclusive Q is true when exactly one of them is true. True and is false otherwise. Okay, so this is exclusive operation. Now I think these are the basic ones. We can talk about what is known as conditional statements. Conditional statements. So we are given two propositions P and Q. Okay, and we write P arrow Q. So this is the proposition. If P, then Q. If P, then Q. So normally here P is a hypothesis and Q is a conclusion. Okay, or consequence. So this is P arrow Q is false when P is true and Q is false. So hypothesis is true and conclusion is false. Then this is false, right? And true otherwise. This is the first conditional statement, right? So I can make a table here PQ P is true, Q is true, then this conditional statement will be true. P is true, Q is false, then this is false. P is false, Q is true, then this is true. And if both are false, then this is true. So we also write, there are many ways we can write this. P arrow Q. If P, then Q is there. Similarly, sometimes we also write if P, Q. Or we say that P is sufficient for Q. Q if P. We also write Q when P. Okay. Or a necessaries condition for P is Q. Or P implies is Q. Or P only if Q. A sufficient condition for Q is P. and so on. Actually, there are many such, you know. Okay, so there are many such equivalent things are there. Q follows from P. Q is necessary for P. Okay, Q unless negation of P, and so on. Anyway, so the next I'm going to talk about converse, contrapositive, and inverse. Okay, so the first thing, Q implies P is converse of P implies Q, right? Similarly, the contrapositive of P implies Q is negation of P, negation of Q implies negation of P. I think we have seen this in one of the proof in the last class. Okay, so as a tea time problem, I would like to invite you to tell me which proof we were doing this. Next, negation of P implies negation of Q is called inverse of P implies Q. Okay, this is converse, contrapositive, and inverse. Next comes biconditional statements. What are biconditional statements? So P if and only if Q. Okay, this is the proposition. So I can make the truth table for this. P is there, Q is there, P if and only if Q. If P is true, Q is true, P if and only if Q is true. P is true, Q is false, this is false. If any one of them is false, actually, this will remain false. I mean, if one of them is false, then this is false. And if both of them are false, then this is true, right? This is the truth table for biconditional statements. Okay, so these are the basic things I talked about. Negation of P, conjunction of P, disjunction of P, exclusive P and Q, conditional statements, P implies Q, Q implies P, converse, contrapositive, and inverse, and biconditionals. Now I think I can give you some idea about compound propositions. I'm covering all the very basic things. Compound propositions. And let me take an example. So basically, I can give you an example from with respect to the truth table. P join negation of Q implies is P meet Q. So the question is, what happens? Can we say in terms of truth table what happens here? So let us look at the this compound proposition. I'm going to make the truth table for P, Q, negation of Q, then P join negation of Q, P meet Q, and finally our final statement P join negation of Q, okay, I think negation of Q implies this P meet Q. So this is the conclusion. If this is true or false, so depending upon that, we can arrive at the conclusion. So many times these truth tables, we are writing true and false. So in some books you will find binary notations 1 and 0 as well, So if P is true, Q is true, then negation of Q will be false. P join negation of Q will be true. We can do from the truth tables. P meet Q will be true, and then this will be true. If this is true, this is false, this is true, this is true, false, false. If this is false, this is true, negation is false, this is false, this is false, this is true. If both of them are false, P and Q, then this will be true, this will be true, this will be false, this will be false. So by truth table, we can also express these basically compound propositions. So one more thing, one interesting thing is there. So as I mentioned, these true and false can be mentioned by 1 and 0 as well. In some books you will find that, rather than writing T and F all the time. And so there is some precedence of logical operations. If we are given a larger compound proposition, which one we should evaluate first? So there is a precedence, so we can mention that. Of logical operators. Okay, so operator and precedence. So we can have negation is the first precedence, then meet is the second one, join is the third, then implies is fourth, and if and only if fifth. So this is the order in which we do the precedence. So when we evaluate compound propositions. Now I think we covered again. I'm just going to tell you what we have done till now. I gave you the definition of idea of proposition, gave you some examples. I talked about negation of P, truth table, then negation of P. We looked at conjunction proposition, we looked at disjunction proposition, exclusive proposition, conditional statement, P sorry, P implies is Q, converse, contrapositive, and inverse, biconditionals, compound propositions, and precedence of logical operations. Now we are ready to describe what is known as propositional equivalence. Propositional equivalence. Okay, so what does that mean? A compound proposition that is always true no matter what the truth values of the propositions that occur in it is called tautology. So I think what is tautology? A compound proposition that is always true no matter what the truth value of the propositions that occur in it is called TAU tautology. Okay. Similarly, a compound proposition that is always false is called contradiction. And a compound proposition that is neither tautology nor a contradiction is called contingency. Okay, so these are some basic definitions. So let me give you some examples. Okay, P join negation of P is tautology. And P meet negation of P is a contradiction. So we can verify it by looking at the truth table. P negation of P, P join negation of P, P meet negation of P. So if P is true, negation of P is false, the join will be true, and this is false. If this is false, this is true, and this is false. So no matter what is the values of these variable P, right? This is always true. So this is tautology, and this is always false. So this is a contradiction. Okay. Okay, so now I think we are ready for the logical equivalences. How do we show that? Logical equivalences. Okay. So two compound propositions P and Q, they are compound propositions P and Q are called logically equivalent if P, if and only if Q is a tautology. Okay, so it is true. Okay, so let me show you that negation of, let me show you an example here. Negation of P join Q and negation of P negation of Q. They are logically equivalent. So basically, we also denote these things logical equivalence by P like this, or sometime we write it like logically equivalent. P and Q are logically equivalent. Okay, in fact, I should mention to you that negation of P meet Q is same thing as is logically equivalent to negation of P join negation of Q, and negation of P meet Q same thing as negation of P negation of Q. These are known as De Morgan's law. Okay, so I can now make the truth table and verify that this is the case. P Q P join Q, negation of P join Q, negation of P, negation of Q, negation of P join negation of Q. Okay, so we can make the table here. P is true, Q is true, join with true, and I can compute the negation of P. This will be false. Negation of P will be false because P is true. Q will be false, and this will be false, and this will be false as well. If this is true, this is false. This is true, this is false. This is false.
Sir, last two columns.
1 minute. I think there is some problem, right?
Yes, sir. In last line should not be there. There is only one column at last.
This is, oh yeah, this line should not be there, right? I'm not
Yes,
sure if
sir.
I can delete it actually. 1 minute. Okay, maybe I can just delete it. This is not there. Yeah, I think I can rewrite it actually. Don't worry. Negation of P join negation of Q. Correct. So this is false. True, false. Correct?
Hello, sir.
Yes?
In last line, you need me to include two conjunction disjunction to prove first result.
Hmm?
Here you took joint, so For proving the De Morgan's law, you have to take.
So I am actually proving the logical equivalence of these two relations here.
Sir, the last column should be negation P, junction negation Q.
ये ऐसे होगा, right?
Yes.
Correct?
Yes.
Bas.
Yes.
So now this is false, true, true, false, true, false, false. When writing so many things, I'm always doing mistakes, anyway. False, false, false. This will be true, 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 true. So you can see that this column and this column, right? They are matching, right? They are matching in the truth values, false, 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 true, false, 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 true. So they are logically equivalent, right? Okay. Now I think I can maybe give one more example of the logical equivalence. P implies Q is same thing as negation of P join Q. So P, Q, negation of P join Q, and P implies Q. So I have to show that these two compound propositions are logically equivalent. P is true, Q is true, negation of P will be false because P is true. This will be true, this will be true. This is true, this is false, this is false, this is false, this is false. This is false, this is true, this is true, this is true, this is true. This is false, this is false, this is true, and this is true. So essentially, we have we can see that this and this are mapping. So they are logically equivalent because their truth values are same. Okay. So I think now I guess I can mention some laws here, but rather I will show you rather than I will show you rather than writing it again because it takes a lot of time here. Let me show you. Yes, so I think from these notes which are there, so now you can check that for the distributive law, we can make a similar table. So P join Q meet R is logically equivalent to P join Q meet P join R. And a distributive law, you can see that these two columns are matching. Okay. Similarly, we can generalize these laws, negation of P1 join P2 join ... Pn is same thing as negation of P1 meet negation of P2 negation meet ... meet of negation of Pn and so on. Then we have certain laws like identity laws. P meet true is always is equivalent to P. P join F is equivalent to P. Similarly, we have domination laws, identity laws, idempotent law. P join P is P. P meet P is P. Negation of P is P, which is double negation law. Commutative laws, associative laws, distributive laws. De Morgan's law, we just saw that. Absorption law, P join P meet Q is same thing as P, and so on, right? So negation laws. Okay. Then we have conditionally logical equivalence laws, biconditionally equivalent laws. All these laws are there. I mean, standard tables also given in your book. You may verify them using the truth table. So I invite you to verify some of them using the truth table, you know, as an exercise for today's class. I think that's all for today. So next class, I will show you how from a truth table you can actually write the proposition, you know, on all those calculate simplifications. And I think we will do a couple of more things, you know, and then after that we will be doing the normal forms, and then we'll talk about the quantifiers. Okay, so that's all for today. Okay, so thanks for the class today.
Sir,
Yes.
sir, I have a doubt, sir.
Yes. Bolo.
Sir, exclusive P and Q is inverse of biconditional, right?
Which one?
Exclusive P and Q.
So you verify by the truth table. I'll just say that you try to see it, verify with the truth table right now, because I think till now you know only the truth table, right? Okay.
Yes, sir.
Sir, I think
Yes.
it's inverse of that P implies Q. Like,
Yeah. See, there are so many ways you can use you can actually simplify the compound propositions. I'm going to talk about few of the techniques in the next class, but I think you know, just you know, floor is yours. You know, you can play with these things. You know, I have written some of the laws, and you know, of course you can just play and verify. Right now, whatever I told you about the verification is the truth table system, right? You make the truth table and see if they are equivalent or not, right? Okay.
And sir, I have one question in RSA crypto system.
Yeah. Bolo.
Sir, till today's time, why we are using this simple technique in which we are factorizing n as a product of two prime number? I I mean we can use n as a product of four prime number in which first two prime number can be considered or last two prime number. But why are we using this simple method?
So you are showing why we are using only two prime numbers, right?
Yes, sir.
Yeah, so I mean the system works perfectly fine. I mean you can generalize the system if you and you check that you know if it works or not. So I would, in fact, I would suggest that if you think that you can build a crypto system based on product of three prime numbers, why not? I mean, try and see what happens. Okay, it is entirely up to you. You know, you try and see what happens. Can you make the system? See, RSA crypto system is I would say that is the first kind of public key crypto system. After that, there were many more public key crypto systems have been proposed. And now, as I told you, that because of quantum computers, these systems are not safe. And now, National Institute in US is suggesting you know, in the post-quantum crypto systems, like coding theory-based crypto systems, code-based crypto systems, or lattice-based crypto systems, which are much more advanced. And I think you can find this in your, you know, some of your cryptography courses when you read, when you look at the cryptography courses. Okay.
So, sir, these are not safe in today's time. So, why are still companies using this system?
Because still there are, it has not been broken till now. Because the quantum computers are there, but actually, you know, it's still the you know, the quantum computers right now which have been developed by the companies are of smaller qubits, you know, like, you know, so if you have enough qubits quantum computer, then it will be broken. So right now people are using it, because still we know that more efficient systems are not there. So we increase the key size, the number of bits used, and so we know that that is safe. We require more, quantum computers with more qubits, which can break the things. So those things people are developing. Still, it is not there. So I hope is after a few years from now, certainly nobody will use it. And moreover, I think now people are developing the next generation crypto systems, which will be secure. Even if the quantum computers are there, they will remain secure. Okay.
Okay, sir. And sir, I have one doubt in algorithm of that you, sir, in this in that algorithm, you said that first B declares it private keys. That is exponent A and N.
Right.
So, sir, where after what time duration it will change?
What do you mean by time duration?
Means for what time duration these private keys E and N are fixed.
No. So now what happens? This is implemented through a third party. There are companies which will actually manage these things. For you. Okay. It's not about the time system. So basically, they try to update their RSA certificate after certain time. So they use it for, say, maybe few years or few months or whatever, and then if they feel that they need to increase the key size, they go a bit further. So mostly the standards are 2048 bits right now. Okay, that are used. So there are standards actually. So once you build a crypto system, of course there has to be standard that has to be followed, because everybody should agree on those things. Okay.
Okay, sir.